Okay, 2.6 combinations of transformations. So when a function consists of more than one transformation, they're described and applied in the following order. Okay, so this is exactly like bed mass. Okay, stretches, compressions, and reflections have to be applied first because those transformations were dividing or multiplying, right, in the mapping notation, then horizontal and vertical translations, because again, like those are adding and subtracting. Okay, so we have to apply them in this order. So describing transformations of functions. Example 1, describe how the graph of each of the following functions can be obtained from the base graph and state the mapping or the point notation. So the base graph of this one is just f at x, or y equals f at x. So if we look at the positions of these transformations, we are going to get a transformation with this negative sign. Then we're going to get a transformation with the 2, and we're going to get a transformation with the 4. Okay, so all of these are around the x, so all of them are going to affect the graph horizontally. Okay, the negative is going to be a reflection in the y-axis. Because remember, if it flips over the y-axis, the x numbers are changing. Okay, the 2 is going to be a horizontal compression by a factor of 2. And the positive 4, well, it looks positive. That's really negative. So we're going to go left 4. Okay, in our mapping, we're going to go from x, y, and how we would map this is every single x value is going to be multiplied by negative because of the reflection. Okay, it's a compression by a factor of, well, we can say 2 or 1/2, doesn't matter. So since it's a compression by a half, we're going to put negative 1/2 x, and then we're going to subtract 4 since it goes left 4. And all of these have to do with just the horizontal. Okay, the y is actually going to stay the same. Okay, so the next one, this is the base graph here is y equals x squared. So this is actually a combination of both the x and the y, so horizontal and vertical transformations. So we're going to go in order. For the 5, we're going to have a vertical stretch by a factor of 5. Okay, this negative 1, this is going to the right one. Okay, that's obviously affecting the x. Right one, yeah. Vertical, that's obviously affecting the y. Okay, and then the 3, that's going to go up 3. So that's going to affect the y as well. So when we take a look at the mapping, okay, first we want to say what's affecting the x value. Well, the x is just going to the right one. So exactly how we would say it, right 1, we would add 1. Now the y value, there's a vertical stretch by a factor of 5. So we're going to multiply every single y value by 5, but then it's also going to move up 3. So then we're going to add 3. Okay, for the c, when we're given a function like this, and this is just the y equals f at x general function, okay, what we have to do is we have to factor first. So we actually can't list the transformations of this graph until this x is beside the bracket. So what we're going to do is we're going to divide out the negative 3 just from inside the bracket, and that's going to give us our bracket with the x there. okay, and then plus 2. Okay, so in a situation like this, you're going to get like the -3 correct. But if there's a translation here, this is going to be backward and it's going to be a different number. So that's where you have to factor out the entire coefficient of x. Okay, so based on this one, we're going to go in order. So this 1/2 is a vertical stretch. By a factor of, this is not a stretch, this compression. Sorry, it's 1/2. Vertical compression by a factor of 1/2. Okay, the next transformation is this negative sign. So this is a reflection in the y-axis. The next transformation is this 3. So all of these numbers around the x are going to be the opposite of what they look like in the equation. So it looks like a 3. So this is going to be a horizontal compression by a factor of 1/3. Okay, and then this one's going to be left 2. Okay, so vertical affects the y. I'm just making a quick note. Reflection in the x or the y-axis is going to affect the x's. Horizontal affects the x's, and then left 2 affects the x's. So our mapping notation, we're going to go from our normal xy, and these 3 are going to affect the x's. So reflection is a negative, compression by a third is a third x, and then left 2 is -2. And now the y, there's a compression by a half, so 1/2 y. So this is going to be our mapping notation. Okay, next one. So the 5 is already factored out, so let's go right into it. This negative sign is going to be a reflection in the x-axis. This 4 is going to be a vertical stretch by a factor of 4. Okay, the 5, so again, anything around this x in here, it's going to be opposite. So this is going to be a horizontal. This is going to be a compression by a factor of 1/5. Okay, we're going to go to the right 2 and down 3. Okay, so we're going to take our mapping. I'm just going to make a little note of whether it affects the x or the y. So reflection in the x-axis is actually going to affect the y. Vertical stretch, y. Horizontal, x. Right 2, x. Down, up and down affects the y. So what affects the x? We have horizontal compression, so 1/5x, and then right 2, plus 2. And now what affects the y? -4 minus, y minus 3. Okay, last one. Let's go in order. So this is a rational function. So we're going to have a reflection in the x-axis. Okay, the 2 is a vertical stretch by a factor of 2. Okay, the 3, and this is good because the 3 is already factored out of the bracket. So this is going to be a horizontal compression by a factor of 1/3. Okay, we're going to go to left 4, and we're going to go down 7. Okay, reflection of the x-axis affects the y. I'm going to change color. Vertical stretch, vertical is up and down, it affects the y. Horizontal affects the x. Left x, down y. Okay, so our mapping, what affects the x? We have a horizontal compression by 1/3, so 1/3 x, and then we're going to move it left 4. And in regards to the y, we have -2y minus 7. Now what we're going to do is we're going to graph transformations of functions. Okay, so example 2, for each of the following functions, what we're going to do is we're going to state the mapping notation, we're going to sketch the function, and then we're going to state the domain and range. Okay, so we have the first equation, we have this. So it's a root function. Okay, so I already filled in like the root function for you, 0, 0, 1, 1, 4, 2, 9, 3. Okay, and now here are the transformations on it, and we'll go in order. Okay, so actually, I'm going to show you how I group these. So everything around the x here is going to affect the x value. So what I'm going to do is all that happens here is it's going to the left 3. Okay, so the mapping notation for the x's, it's going to go x minus 3. Okay, and the front and the back are going to affect the y. And the front and the back, like the y values, they're straightforward. -2y minus 1. -2y minus 1. Okay, this is a reflection in the x-axis. Vertical stretch by a factor of 2 and down 1. So these two mappings I'm going to put, so this is going to be our x column, see, x, y. Okay, these map onto x minus 3 and 2y minus 1. So every single x value here, we're actually going to subtract 3 from. So 0 minus 3, 1 minus 3, 4 minus 3, 9 minus 3. Now, every single y value, we're going to multiply first by -2, and then we're going to subtract 1. So in other words, we're basically taking this number and saying, okay, -2, 0, minus 1. -2, 1, minus 1. -2, 2, minus 1. -2, 3, minus 1. That's how we apply these transformations on every point. So for the first one, we get -1. Then I get -3. It's -4, -5. That's -6, -7. So our original function, let me just do the original in like purple, is 0, 0, 1, 1, 4, 2, 9, 3. Okay, that's our original, our parent, our base function. So y or f at x equals root x, okay? As for our transform function, we're going to plot it at -3, -1, -2, -3, 1, -5, 6, -7. Okay, and these are going to connect like this. Because this point here corresponds with this point here, this is going to be our quote unquote, like the start of our graph. Okay, so there's no arrow on that end. Okay, and we know that those two correspond because this point here, 0, 0, corresponds to -3, -1. So our domain, start with the XER such that, and range start with the YER such that. So what we're going to focus on here is, did we reflect anywhere? Okay, so we're going to focus on our starting point, So like the starting point, and then did we reflect? Okay, two things we want to focus on for domain and range. So our quote unquote starting point, for the x it's -3, but this time we're actually going, for the x's, right, we're going increasing to infinity because we can see this arrow. So x is going to be greater than or equal to -3. Okay, and our y value is going to be here, it's -1, right, the start value. But this time we reflected, so the y is actually going to go down to -infinity. So y is going to be less than or equal to -1. Okay, B, y equals 1/2 x minus 3 squared plus 2. Okay, so we know that the base function here is the x squared function. Okay, we can write that with mapping function notation as well. Okay, so for the mapping notation, again, everything around the x is going to affect the x. So this is going to the right 3. We're going to go x plus 3, okay, because it's going right 3. If you need to jot that down on the side of your paper, that's okay. Now, everything before and after, not in brackets, is going to affect the y. And we're going to take this as is. So 1/2 y plus 2. Okay, so in our chart, our mapping, every x value that we have, we're going to add 3 to it. And every y value, we're going to multiply it by 1/2, and then we're going to add 2. Okay, so let's do all the x's first. So every value here, add 3 to it. So -2 plus 3, -1 plus 3, 0 plus 3, 1 plus 3, 2 plus 3. Okay, and every y value here, we're going to half it and then add 2. So in other words, and just so that you can visually see, it's going to be 1/2 of 4 plus 2. Okay, so I get 4. The next one's going to be 1/2 of 1 plus 2. So this is 1/2 plus 2, it's like 2.5, 2.5. Okay, 1/2 of 0 plus 2. Well, it's just 2. Okay, 1/2 of 1 plus 2, it's going to be the same, 2.5. And then the 4 is going to be 4 as well. Okay, just remember that these are symmetric about the vertex, okay? So our original graph in blue, I get 0, 0, 1, 1, -1, 1, 2, 4, -2, 4. And then we just know, like common knowledge is that it goes through 3 and -3 and then like 9. Okay, so that's the original function. Okay, our graphed function is going to be like this, 1, 4. So 1, 4. I want a different color. Here we go. 2, 2.5. 3, 2. 4, 2.5. And then 5, 4. Okay, and simply we see that this was compressed, right? So it's kind of like in the range that we graphed. This is vertically compressed, it's shorter. Okay, and then also the vertex moved to the right 3 and up 2. Okay, right 3 up 2. And we can see that because it's vertex form, right? 3, 2. So domain and range. Our domain and range for this is going to depend on where the actual vertex is, and then whether or not we open up or down. So actually, the domain is XER. It's going to hit every number to the left and right. It's going to go from -infinity to infinity. And the range is going to depend on that optimal value. So that like if you're doing HK, so in our case now we're calling it C, but we're going to start, quote unquote, start at this 2, and we're going to go up. So y is going to be greater than or equal to 2. Now we're going to deal with an example with a rational function. Okay, so we get -1 over x plus 3 minus 2. Okay, so what's the mapping notation? So let's see what affects the x's. So anything right here in this denominator is going to affect the x's. So in this case, x is going to move to the left 3. So x minus 3. Okay, and then the number up here and the number on the side, those are both going to affect the y's. So we're going to reflect the y and then subtract 2. Okay, so -y minus 2. Okay, so x minus 3 minus y minus 2. Okay, if we were to plug in -1, so we would get -1 minus 3. I get -4. Now 1 minus 3, I get -2. Okay, now for the y's, I'm going to sub in -1. So it's negative of -1 minus 2, so that's 1 minus 2, I get -1. Okay, and I get negative of 1 minus 2, so I get -3. Okay, now for the horizontal asymptote, the thing is, our original horizontal asymptote is here that y equals 0. So our horizontal asymptote is just going to actually be the shift up or down. So we know that we're going down 2. So our horizontal asymptote is actually now y equals -2. And we don't need that. Okay, and what about our vertical asymptote? So our original vertical asymptote is x equals 0. Okay, and this is going to be affected if it moved right or left. So we're actually moving left 3, so our vertical asymptote is going to be -3. 1, 2, 3. So our new vertical asymptote is x equals -3. Okay, so our original function is going to be graphed, and when we use like quadrants loosely, we're graphing like this is the intersection of our vertical and horizontal asymptotes. We're graphing in the kitty corners, and then we'll graph our function 1 over x. Now, when we graph our transform function, we have x equals -3 and y equals -2. So this is our new like fake quadrants, quote unquote quadrants. So what we're going to see here is that our graph is going to have to lay kitty corner. So either these two or these two. So we have -4, -1, and then -2, -3. Okay, so that works. I just went straight off of these transformed points, and that works. And then we're just going to use our new asymptotes. Okay, maybe do those in purple so that they match our graph. Okay, and this one is y equals -1 over x plus 3 minus 2. Okay, so you can see the intersection of our asymptotes here is 0, 0. We move down to left 3, and now that's our new intersection. Okay, and we also reflected. So instead of being kitty corner this way, we're now kitty corner this way. Okay, for domain and range, I always set it up. And I always know for a rational function, it's going to be every single number except for the asymptote. Okay, so in regards to x, check this out. Our vertical asymptote is -3. So x is not going to equal -3. Our horizontal asymptote, see the y? So convenient. It does not equal -2. Okay, and you can cross-reference that with the graph. Okay, in the last example, the following graph, let's just name it f at x because it's like a chunk of 1, 2, 3 different lines. Okay, so first state the mapping notation and then list major points. So when we talk about major points, we're actually going to talk about like end points, which are these two, and then turnaround points, which are these two. And we're actually going to go in order where we're going to go from 1, 2, 3, 4. So they may not look like numerical order, but we're going to go in the order where we would have to connect these. Okay, then we're going to sketch the graph with these transformations on it. Okay, you notice how there's an f here, that's the general function. So first of all, this mapping notation, it's going to go left 3. So we're going to subtract 3 from the x's. Then we're going to go 1/2 y minus 2. 1/2 y minus 2. Okay, so the points, -3, 8, and then it goes to 6, 4. Then it goes to -5, -3. Then it goes to 0, -6. Okay, so let's take every single x value and subtract 3. So -3 minus 3, 6 minus 3, -5 minus 3, 0 minus 3. Now for the y's, let's half them and then subtract 2. Half of 8 is 4 minus 2. Half of 4 is 2 minus 2. Half of -3, so hard ones, I might have to write down. So this is -1.5, and then minus 2, I get -3.5. Okay, half of -6 is -3, and then minus 2, so I get -5. Okay, so let's actually graph this. -6, 2, 3, 0. So those two are going to connect. Okay, right, we're going in order. -2, -3.5. So connected here. -3, -5. I have to fix this. I knew this didn't look right. This number, -5 minus 3 is -8. So sorry. This one here is -8, 1, 2, 3.5. That looks better. And then -3, -5 is correct. And I kind of just saw that just because it didn't look right. Let's blur that out. Okay, it didn't look like the same, like this kind of looks like a Z, and now it still looks like a Z. Okay, so domain and range. So this is a continuous function because we don't have to lift our pencils when we draw it, right? It's just kind of like a Z. So x is an element of the real number system such that what two numbers is x going to be between? So the very most left number is -8 and the very most right number is 3. So x is going to be between -8 and 3. And the range is going to be between the bottommost number is -5 and the topmost number is 2. Okay, so y is going to be between smaller number -5 and 2.